Hello students, this is Poonam. In my earlier video, I have explained logical instructions from instruction set of 8051. Now I am going to explain Boolean variable manipulation instructions from instruction set of 8051. So let's start with it. So here is a list of various types of instructions which belongs to Boolean variable manipulation instruction. First one is CLR bit, that is nothing but clear bit. This will clear the indicated bit which is there in the instruction. We'll take one example of it. Say suppose the instruction is CLR P2.3. So port 2 has been written with ADH, say suppose some value ADH. ADH can also be written as 1010, that is A, that is 10, and D is 1101. So clear P2.3 after execution will clear the third bit of this port. So this one is 0th bit, this is first bit, this is second bit, and this is the third bit. So third bit, which was earlier 1, after the execution of instruction CLR P2.3, this bit will be cleared and it will be made 0. So it will become 1010 as it is. The third bit will become 0 and other remaining bits as it is. So this was the first instruction from the group. Second instruction is set bit. In this set bit, this instruction will set the indicated bit. Suppose example is set P2.3. So whatever value are there, whatever value is there at port 2, the third bit from that value will be made 1. Third instruction is CPL bit. CPL is nothing but complement bit. So this instruction will complement the bit variable. Example CPL P2.5. So say suppose P2 is having some value like 10100101. We will take same value. Say suppose same example we'll take 10101101. So if CPL P2.5, if I am writing, the fifth bit will be complemented. So this is 0th, first, second, third, fourth, fifth. So if the value is this, the after execution CPL it will become 1000. So this bit is complemented, which is actually there in the instruction. So this CPL P2.5 will complement the fifth bit from port 2. Next instruction is ANL C comma source bit. So this is logical AND for bit variables. This instruction will logically AND the carry bit and the specified source bit, and the result is stored in carry bit. We will take one example of it. ANL C comma accumulator dot 4, and if carry is equal to 1, we will consider that A, that is accumulator, is having value 11H. So 1 is represented as 0001, that is first one, and the other one is 0001. So this accumulator is holding this value 0001. So because of this instruction ANL C comma accumulator dot 4. So the fourth bit is, this one is 0, this one is first, this one is second, this one is third, and this one is fourth. So fourth bit is 1, and logical ANDing with C, that is also 1. So ANL 1 comma 1 will give you value 1, and that result is stored in carry bit. So carry will become now 1. We'll move to the next instruction, that is ORL C comma source bit. This is logical OR operation for bit variables. This will logically OR the carry bit and the specified bit, and the result is stored in carry bit. We'll take example of it. ORL C comma slash. That slash is nothing but bar or complement of accumulator dot 4. Now we will consider that this carry bit is 1 and A is holding value 11H, which is represented like this. So if this instruction is executed, the instruction ORL C comma bar accumulator dot 4 will logically OR the contents of carry with the complement of accumulator bit 4 leaving. So the fourth bit is 0 to 3 and fourth bit is 1. So complement of this 1 is 0. So C is 1 ORing with 0 will give you value 1. and the result is stored in carry bit. So C will become 1. The next instruction is move destination bit comma source bit. So this is called move bit data. This will copy the source bit into the destination bit. There are two types of combinations for this. First one is move bit comma C. We'll take one example directly. Move accumulator dot 3 comma C. Say suppose C is 1 and A is 11H again. 11 means 0001. Then the instruction move accumulator dot 3 comma C will copy the contents of C to the third bit of accumulator. Say suppose C is having 1 and accumulator's third bit, whatever is the value, in this case the accumulator third bit is 0 because we have taken that A as 11H, so 0001 and 0001. So the third bit is 0. Now that third bit will be made 1. So the accumulator is now holding the value 0001 and 1001. So which was initially 11H, now it will become 19H. Now the second combination we will see, move C comma accumulator dot 4. So whatever value is there at the fourth bit of accumulator, that will be copied to the C bit. Let's talk about now program and machine control instructions. In that there are some instructions which are unconditional jumps. So 8051 supports the following unconditional jump instruction. First one is A jump address 11, L jump address 16, then S jump rel, and jump at the rate A plus dptr. We will see all this unconditional jump in detail. The first one is A jump address 11. This is nothing but absolute jump. This instruction transfer the program execution to the indicated address, that is A jump label. We will directly take the example so that you will understand. Suppose the instruction is A jump L7. So my instruction is A jump L7. Instead of this address 11, I'll write A jump L7. Now the label is L7. Now that L7 is at some program memory location which is 053H. So that label is at 053H 37H location. And the instruction A jump L7 is at 0678H. Remember, the instruction is at 0678H, but the label L7 is at this location, that is 0537H. Now, after execution of this instruction, what will happen? After executing the instruction will load the PC, that is nothing but program counter, with the memory location of L7, so 0537H. So this instruction will load the program counter with the location of the label which is specified in the instruction, so that from there the program execution will begin. Now the second type of unconditional jump is ljump address 16. This is nothing but long jump, and this instruction causes an unconditional branch to the indicated address by loading the high order and low order bytes of PC respectively with the second and third instruction bytes. So what this is going to do, the destination may be anywhere in the full 64 KB program memory. So this is long jump, so the destination can be anywhere in the 64 KB of program memory. We'll take example of it so that you will understand. Example is L jump L7. Now remember the instruction L jump L7 is at location, say suppose 0537H. The instruction is at this location and L7 is at this location, which is 5678H. Now what this will do, this will set the PC, or this will set the program counter at this location, which is location of L7. So this will work same as that of absolute jump, but the only difference is the destination may be therefore anywhere in the 64 KB program memory. So it is called as long jump. Now we will move to the next type of jump, that is SJMP REL. So this is nothing but short jump. The program control branches unconditionally to the address indicated. The branch destination is computed by adding signed or relative displacement in the second instruction byte to the PC after incrementing the PC by twice. So the only limitation in this is the jump range is limited because it is short jump. So the only limitation is that the jump range is limited from -128 to +127 bytes. The destination range allowed is from 128 bytes before the instruction and 127 bytes after the instruction. So that is why it is called as short jump. Next instruction is called jump at the rate a plus dptr. So this is nothing but jump indirect. This instruction adds the 8 bit of unsigned contents of accumulator with the content 16 bit dptr, and the result is loaded into the program counter. So we will take simply example of it. The example is, say suppose jump at the rate a plus dptr. Let us consider a is 30h and dptr is 1000h. So a plus dptr will become what? 1030h, right? Initially program counter is at 0500h. Now after execution of this instruction, the program counter will be loaded with this, which is 1000 plus 30, which is 1030h. So program counter will become 1030h. So that execution of the program will start from 1030h, which was initially at 0500h. So these all the things which we have discussed till now were nothing but unconditional jump. Now we will see some of the conditional jumps. Conditional jumps transfer program if the condition is satisfied. And all conditional jumps are always short jumps. So the addresses are within -128 to +127 bytes of the contents of PC. So we will see all the conditional jumps. First one is JZ, that is jump if 0. Means this will be executed if A is equal to 0. Jump if A equals to 0. Second one is JNZ, that is jump if A is not equal to 0. Third one is DJNZ, that is decrement and jump if not equal to 0. Next is jump if JC, that is jump if carry, means jump if carry equal to 1. And this is jump if not carry, that is jump if not carry means jump if cy equals to 0. Next one is jump if beat, means jump if b equal to 1, and jump not beat, that is jump if beat equal to 0. Next one is JBC, that is jump if beat equal to 1 and clear bit. This C stands for clear bit. Next one is CJNEA comma data, that is jump if A is not equal to data. And last one is CJNE register comma data, means jump if byte is not equal to data. Thank you.